Alrighty then, let's move on to the second page of that marvelous package on scientific processes. This next little section focuses primarily on the hypothesis. And I know the top of the second page there and following, you could read it. You are capable. But human nature is just a little bit bent, and given the option of reading it or not reading it, I know what I'd be doing if I was your age. I wouldn't look at it. So guess what? I'm going to read it to you. Do feel free to follow along. So how are hypotheses written? Hypothesis statements. By the way, notice the difference between singular and plural. A single hypothesis, more than one hypothesis, we call them hypotheses, right? Anyhow, they're formalized statements that not only make a prediction, but suggest a method for testing that prediction experimentally. If we were simply to write a statement such as Miracle-Gro will cause increased plant growth, by the way, Miracle-Gro is a commercial plant fertilizer, makes your plants grow all nice and healthy. We are simply making a prediction without suggesting a means for testing it. By writing a formalized hypothesis statement, we not only predict the outcome of an experiment, but suggest a means for carrying out that experiment. So let's look at a couple of examples. We have two of them, in fact. I think we should number them. Let's call this puppy number 1. If skin cancer is related to ultraviolet light, then people with a high exposure to UV light will have a higher frequency of skin cancer. Yeah, you notice the words in bold, in particular the if, then. Okay, there is no law of the universe that actually states that you have to use the if-then format in a hypothesis. It's not a bad way of organizing your thoughts, and therefore I recommend it. Point is, both of these statements can be broken into two parts. Take a look at the second one. If leaf color change is related to temperature, then exposing plants to low temperatures, and by the way, it could be high temperatures, will result in changes in leaf color, as long as you don't go too high, right, or too low. The then component makes a prediction, while the if component outlines an experiment for testing that prediction. Each of these statements also clearly outlines both the dependent and independent variables. You have heard of the dependent and independent variables. In general, in an experiment, the thing you're controlling is the independent variable. The result of your experiment, the thing that is changing in response to that, it's dependent on that. It's the dependent variable. So for statement number 1, this puppy right here, we would say that the UV light is the independent variable, and skin cancer would be the dependent variable. Why don't you try number 2? In statement 2, which do you think is the independent variable, and which do you think is the dependent variable? What do you think you have control over? I would say you have control over, why do I feel I want to switch colors? Let's go to this one. Temperature, yeah. So temperature is the independent variable, and in response to that change in temperature, you are going to get leaf color changes as the dependent variable. Makes sense? I think so. So you now have an opportunity to rewrite the following statements in an if-then format. In other words, as a hypothesis. So initially, this statement is bacteria growth can be affected by temperature. Yeah. I think we should write down the word if. Bacteria growth, basically just restating this. If bacterial growth can be affected by temperature, that's a can by the way, affected by temperature. What we need here is a computer program that recognizes printing or handwriting that sucks and actually turns it into beautiful script. It's probably out there. This is PDF annotator, by the way. So if bacteria growth can be affected by temperature, then increasing the temperature, I'm just going to abbreviate it, temp, will lead to increased bacterial growth. Yep. Number 2, plant growth may be affected by the color of light. So I would suggest, again, the if-then statement. If plant growth is related to the color of light, heard of RGBIF, red, green, blue, all that good stuff, then plants grown. By the way, you feel free to draw in the lines. I'm finding that a little difficult. So plants grown, pick a color, in pink light. Could have been purple, could have been any other color. Will grow faster. Then you could grow a plant under normal white light, normal light, which of course is a combination of all wavelengths, and you could grow your testing plants under, say, pink light and check their height and see which one does actually grow better. By the way, light is just part of the electromagnetic spectrum from very long wavelengths, things like radio waves and ultraviolet, all the way down to tiny little waves with high energy, things like gamma, X-rays, etc. Right in the middle is what we call color. This is the only wavelength that our bodies are actually capable of detecting, right? And it's a good thing. We are made to experience a beautiful world, and the skies are blue and all that good stuff. Let's see. Number 3, number 4, number 5. I think you should do those on your own. We will see that you've done it during your hot seat. Let's move on. To make a scientific hypothesis, you must attempt to identify a possible cause and effect relationship. Right. So color of light affects plant growth. Temperature affects something else, leaf color. This relationship must be testable in order to be considered a hypothesis. So you might say that brushing your teeth on the planet Venus will keep you from having cavities. May be true, may not be true, but guess what? It's not testable. Therefore, I would not consider that a good hypothesis. Scientists often use hypotheses because they lead to conclusions. And then this lovely little statement here. A hypothesis is often stated in an if-then format. For example, if a plant is given vitamins, then it will grow faster. The hypothesis has a cause, giving vitamins to a plant, and an effect, the amount of growth. To test the hypothesis, an experiment should be used that compares plant growth with vitamins to plant growth without vitamins. The growth without vitamins is called a control. Just knowing how much plants grow when vitamins are added tells you very little about how effective the vitamins are at stimulating growth. The control lets you determine how much faster, if at all, the plants grow. So make sure in any experiment you ever do that you have a control. And the control is there so you can compare. In each of the situations below, complete the tasks that follow the description and the graph. Number 1, you see this beautiful graph. Graphs are so useful in science because it is a visual representation of how two variables interact with each other. This, of course, is the y-axis. Notice it's the bacterial population. We're going from 50 to 500, and notice it's times 100. So 50 times 100, 100 times 100, etc., just because we don't want to have to write a huge number out here. That bacterial population is changing in relation to what you control, the days. This is the independent variable. The y-axis is always the independent variable. Notice the line. The line tells us something. The line gives us a representation that the population changes over a period of 24 days, and you see which days it's the biggest, which days it's the smallest, etc. So the questions: what does that graph allow us to know about this experimental situation? Number one, I think we can come up with a hypothesis. We're looking at mascara growth in bacteria over a certain number of days. I mean, I gotta mention again, I mean, why do women wear that black tar-like substance on their eyes? I don't know, especially if it's showing to contain a whole lot of bacteria. But then I'm not a female, right? So back to the hypothesis. I think the first word should be an if. Right. If bacteria, yeah, for some reason or other, don't want to get going here. So if bacteria is allowed to grow on mascara, what do you think the next word is? You're right. Big then. Then the population of bacteria. I don't actually need to repeat it, but I mean, it would be nice. We'll just say the population will increase over time, and that is exactly what you see as we go from day 1 to day 2, 3, 4, 5. You actually see that line increasing in slope and number of bacteria. So by looking at the graph, we should be able to identify the dependent and independent variables. So I see on the x-axis the thing that you are controlling. You're controlling the time, right? The number of days. On the y-axis, you'll have the independent variable, the population of bacteria that are growing. So, dependent is the bacterial population, and the independent variable would be the time, like days. In other words, y-axis, x-axis. So, presumably there are a whole lot of other variables that should be controlled in this experiment, so we know that the only factors that are involved are time and bacteria growth. I would mention one, temperature. I dare to say if you carried out this experiment in the north of Canada, let's say on the Inuit, those very cold temperatures, you'd probably see a reduced population growth. How about things like the light or the dark? Type of mascara. Did you get it for $48 at Nordstrom? Or did you get it at the dollar store made in China? Now, no offense to China. If you have your heritage in your country of China, the only reason I mentioned it was because there was a news item a while ago that actually did show that some of the mascara products that were being imported from China were high in various heavy metals, and yeah, I wouldn't trust the contamination or lack of it in that product. I would say we should also keep control of the amount or volume of mascara. For some reason or other, this pen is causing me pain. Let's say Susie puts it on carefully, very small quantities, whereas Magdala, she spreads it on with a knife. In other words, you got two massive amounts of mascara. You know what? There's probably a whole lot of other ones here. We will not labor the point. I think you get it. Let's look at number 2. A jar is filled with various amounts of water. let's draw a jar. This is my nice jar. And on our first trial, we basically put this amount of water in there, right? This is water. And then for some reason or other, we put the lid on it and decide to roll it and see how far it goes. How fascinating kind of experiment you just want to do. I know. The thing that's going to change, of course, in all of these is the mass of that jar. As you put more water in it, you're going to notice that it changes. For some reason or other, it doesn't want to just stop like right on the graph. Yeah. So if we have 200 grams of water, it's going to go this far. If we have 220 grams of water in the jar, it's going to go this far, etc. So, what do you think a good prediction and hypothesis might be for an experiment like this? I'm thinking, my favorite word, if the mass of the jar is increased, of course you could say by adding more water, then it will roll farther. Ta-da! Easy thing to test, isn't it? Right. So identify the independent variable. I mean, the easy thing to do is look at the x-axis, mass of the jar. That's got to be the independent variable. Y-axis has to be the independent variable. But it's probably better to think about it. The thing you are controlling is the independent variable. So that would be the mass of the jar. And that, of course, is gained by adding in water. The dependent variable is the roll distance, length, whatever you like. Then we have to be able to read that graph, right? I think that comes up in the last one. But first of all, identify variables that should be controlled. I would say, how about the force with which you roll the jar? Let's say Jim Bob is like a world-class bowler, and he just takes that jar and he just hucks it down the hallway. I'm thinking he's going to get a longer distance than our friend Magdala with all the mascara, who isn't quite sure what to do with the jar, and she just kind of drops it on the floor and doesn't roll it at all. Let's say you're rolling it down a ramp. I would say the ramp angle would matter as well. One guy rolls it down the ramp like that, another guy rolls it down the ramp like that, another guy rolls it down the ramp like that. You're going to get, again, a different velocity on that jar. What about these? By the way, in the classroom, this is the moment where, of course, we would pause and we would say, "Hey, Bobby, what do you think?" And you put your hand up and you say, I know. Surface on which the jar is rolled. Let's say Jim Bob, he's just rolling it on a carpet, and Magdala, she wants to roll it on the gravel, and Billy Bob, he wants to roll it on ice. You're going to get different results unless those are all standardized or controlled. Right, so finally, predict how far the jar will roll if it has a mass of 230 grams. So that's that 230 grams. There's my graph gone. 230 grams, 220, 240, so this is 230. We basically just have to follow up just slightly. 230 would be right there, and then we have to go all the way over to the y-axis. Kind of an estimation there, but I'm going to go for about 23 meters. Do the same thing for the second part of that question. This would be about 23 meters, give or take, and 190 grams. Notice with the less mass, it rolls less, so 15 meters, I would say. If you have a problem with either of those values, you talk to me and we will sort it out, yeah? Okay, last page. depending on the year and state of mind of your teacher. Aha! Guess what we're going to do? We're going to leave this last one for you. When you have your hot seat, basically you're showing this completed package. For that matter, you can do it anytime before the hot seat just to speed up the hot seat process. As a matter of fact, that's better for all paper assignments. If you turn them in to me ahead of time, you can get feedback on it right away, which is so much better. So now I'm going to leave you with this last problem. If you have any problems with it, ask 3, then me. Eventually, you need you to show me your results. Good.